Okay. Should I introduce myself? Yeah, or you introduce? You you give introduction.
Yes, I introduce you.
Okay.
Yes. Ok, pessoal, boa tarde a todos. Eu vou apresentar o professor Changjiang Liu, certo? Então, o professor Changjiang Liu cursou bacharelado em Física pela Universidade de Nanjing University, na China, certo? Ele fez mestrado e doutorado em Física na Universidade de Minnesota, nos Estados Unidos. Depois fez pós-doutorado no Argonne National Laboratory, nos Estados Unidos, e em seguida tornou-se professor na University of Buffalo, certo? Nos Estados Unidos também. Hoje nos dá a satisfação de ouvi-lo falar sobre Superconductivity de potássio, tanto no Oxide Interface and Electric Field Control Magnum Spin Current in Chromium Oxide. Changjiang, thanks for accepting again the invitation to give this talk for yours. Please start your talk.
Okay, thank you. Thank you for the introduction. So now I'm going to present my recent work on the superconductivity at potassium tantalum oxide and also the electric field control of magnon spin current in chromium oxide. So both of these work were primarily done at Argonne National Laboratory, where Juicy also had an interaction with me when he was visiting Argonne National Laboratory. So this is the outline. So I will basically talk about two parts. The first part is about a new 2D superconductor at potassium tantalum oxide, or KTO. And the second part is the electric field control of magnon spin current. So throughout my presentation, if you have any questions, please feel free to ask and then to interrupt my my talk. So you see that both of these materials are oxide materials, right? So then you may wonder, why are we interested in oxide materials? So it turns out that oxide materials can exhibit a very diverse phases, and they can show a great tunability. For example, many oxide materials can show metal-insulated transition, and they can show ferromagnetic, antiferromagnetic ordering, and some of them can also show multiferroic properties. And further, some oxide materials, such as cuprates, can show strange metal and superconductivity. So these are the fundamental physics that oxide materials can exhibit. So upon applications, some of them can be actually very useful for daily applications, such as magnetic recording. And some of those materials can also be used as energy materials, such as lithium battery application and high voltage cathodes. And those materials could be also used in biosensors. So these are the main reasons that why oxide materials are so interesting and very intriguing to investigate them. So the material system I will be focusing on is actually at the first part, as I said, on the oxide interface. So as I just described, the oxide material itself is very interesting. Now, when you bring two oxide materials together at the interface can show even more interesting or exotic properties. So showing on this slide is an example. And people found that when you put a oxide insulate, for example, here it is lanthanum aluminum. So let me bring my pointer. So lanthanum aluminum oxide. So this is a oxide insulator. When you grow this material on another oxide insulator, which is strontium titanium oxide. So both of these materials are insulators. However, when you grow this material on top of the other one at the interface, turns out that the interface becomes very, very metallic and very conductive, and the mobility can be very high. So it turns out that at this interface, there is additional charge carrier generated just due to the special electronic structure or interfacial doping effect. And these charge carriers are confined just within the interface region, very small region. So basically, they become a two-dimensional electron gas. So, and later on, people found that this metallic electron gas can even become superconducting, meaning the resistance can even go to 0 at a sufficiently low temperature. So for this system, the L-lanthanum aluminum oxide or strontium titanium oxide or LLSTO, the superconducting transition temperature is around 200 milliK, so quite a low temperature. But still, this system is very interesting. So now I'm just show you why this system is interesting. As I just mentioned, this interface can show a superconductivity at a low temperature. Now, because the strontium titanium oxide or STO itself has a very high dielectric constant. That means you can just use a backgate electrode, basically deposit at the back of this substrate. Then you can apply a voltage in the vertical direction. So then, in this case, you can use a gate voltage to tune the superconducting transition. So, for example, in this figure, the superconducting transition can be continuously tuned by applying a gate voltage from positive to negative gate voltage. The superconductivity eventually disappears. So basically, this system provides a tunable superconducting transition, superconductivity. So which is not easy to achieve in ordinary superconductor. So another thing is this system can show very high spin orbit coupling. Basically, can be used in spintronics research. People found that the electron gas flowing in this interface can show a very large spin Hall angle, and they used ferromagnetic resonance to basically excite a spin current, and that spin current can be injected into this interface. And then due to the spin orbit coupling, specifically at this interface, it is due to the inverse Einstein effect. Basically, because there is a spin momentum locking. And once you have a spin polarized current, so that spin polarized current can be converted into a net charge current. So eventually, people can observe a large voltage just due to the spin current. And they found that this spin Hall angle can also be tuned by applying a gate voltage. So very interesting. So these are just two examples. Turns out that this interface can show actually quite diverse properties, such as gate tunable insulator to metal transition and insulator to superconductor transition. So large interfacial spin orbit effect. And people also found signatures of magnetism at this oxide interfaces. So the material I was focused on is also basically perovskite, potassium tantalum oxide. So this material actually is very similar to strontium titanium oxide. So this is just a structure, perovskite structure, which has AbO3 structure. So, and now on the right is the top view from the 111 crystal axis. So once you view the crystal axis along the 111 axis, the lattice can form a backward honeycomb shape. So basically, these atoms with different size representing atoms at different layers. So between adjacent layers, the atoms can form a honeycomb structure. So, and people found that this 111 interface can show very interesting electronic structure. So, and they can exhibit some unusual physical properties. So as I mentioned just now, the potassium tantalum oxide is in many ways a cousin of strontium titanium oxide. So for example, here I'm showing you the electronic structure. So in both of these cases, the electronic band structure is derived from the T2G manifold. Basically, it is the mix of dxy, dyz, and dxz orbitals. So the one difference between potassium tantalum oxide and strontium titanium oxide is that in this material, in KTO, the spin-orbit coupling is quite large. In fact, it is more than 1 order of magnitude higher than that in STO. And because of this spin-orbit coupling, the T2G manifold is split by this spin-orbit coupling. You can see here, this delta SO, delta basically spin-orbit coupling, splits the J equal to 1/2 and J equals 3/2 orbitals by as high as 0.4 eV, while for this one, the spin-orbit splitting is only 20 milli eV. So this is quite distinct for KTO. And for KTO, it is also showing very interesting behavior at low temperature, similar to STO. At a low temperature, KTO also showed a very large dielectric constant. So this is because both KTO and STO are incipient, basically incipient quantum ferroelectric materials. Basically, they very close to form a ferroelectric material at a low temperature, but just because of the quantum fluctuation, they eventually just a ferroelectric material. So in STO, people found that one can dope STO, and then the STO can become very conducting at a low temperature. STO can be superconducting at a temperature below 0.5 Kelvin. So people also investigate the doping effect in KTO, but surprisingly, people were not able to see any signs of superconductivity in KTO. So these are the early study of the effect of doping in KTO. So they can see a metallic behavior at a doping level of 10 to the 19th centimeters per centimeter cube, while they did not see any sign of superconductivity at the lowest temperature. However, there's only one report of a weak superconductivity in KTO, which was achieved by using ion liquid gating on the KTO 001 surface. So basically, they use a drop of ion liquid and then use this ion liquid to gate the surface. So they see a very weak superconductivity with a superconducting transition temperature of around 50 millikelvin. So it's a very low, weak superconductivity. So I want to mention that after this report in 2011, no other group has ever basically repeated or reported again for this ion liquid gating measurement on KTO 001 surface. So here I'm emphasizing the orientation. That is because I will show you in a bit the orientation of the crystal of KTO plays an important role in the superconductivity. So now in our case, we just grow a oxide interface using either molecular beam epitaxy or MBE, and also the pulsed laser deposition method or PLD. So in both cases, we deposit a oxide insulate on top of KTO. So for the MBE, we deposit a polycrystalline European oxide on KTO. And eventually, at the interface, we found that the interface becomes a metallic. So for PLD, we deposit lanthanum aluminum oxide, just like LLSTO. Here, lanthanum aluminum oxide forms a amorphous phase, but the interface, actually, I will show you, can still be metallic. So after the material grows, we did some characterization using scanning electron microscopy. So showing on the left is the STEM image, which shows the interfacial region of EUO and the KTO. So you can see a clear interfacial region. And for LL as KTO, we found that, as I mentioned, you do not see the atoms for LL. That is because LL forms amorphous form. But still, we can distinguish a interfacial region. So in both of these cases, the top oxide materials were grown on KTO 111 surface. So we did some further characterizations. For example, here on the top panel, we have the light image STM, which is very sensitive to light atoms such as oxygen. And we found that in the interfacial region, so from left to right is this is the interfacial region, and this is the KTO substrate, so which follows this arrow. You see that. So we found that at the interfacial region, the oxygen weight becomes lower. So that is suggesting that there is a oxygen vacancies forming at the interface. And then using the dark image, which is sensitive to the heavy atom, we see that, so following this arrow, so near the end of this arrow here, the right side, which is corresponds to the interfacial region, we found some additional peak in between tantalum sites. So this means the original potassium site is replaced by europium, which means there is an interfacial doping effect. We think both of these oxygen vacancies and europium doping can contribute the formation of excess charge carriers that is responsible for the conducting interface. So here I'm showing you the measurement of EUO KTO interface. So the measurement is basically performed from room temperature 300 K to about 4 Kelvin. So in both of these samples, so the green color represents the measurement on sample EUO KTO 111. So I emphasize the KTO 111 interface. So it shows a metallic behavior with resistivity or shear resistance decreasing as temperature is lowered. And for EUO KTO 001, it also shows a metallic behavior. So just before showing you the the measurement at lower temperature, I would like to mention that. So previously, people have found that using APIS, which is the angular photo emission measurement, which can probe probe the electronic structure, people found that on the KTO 111 surface, the electronic structure forms a star-shaped or honeycomb-shaped structure with six-fold symmetry. So this six-fold symmetry is a direct result of this honeycomb-shaped crystal structure, and this behavior is consistent with theoretical calculation shown below. So besides of this six-fold symmetric electronic structure, people found that at the interface there is some surface subbands forming, so which is due to quantum confinement, and this quantum confinement is responsible for the two-dimensional electron gas. So now this is the measurement I just showed you earlier on the EO KTO measurement performed at a lower temperature. You see that there are 4 different samples. So all of them are grown at a KTO 111 surface, which has the honeycomb-shaped crystal lattice. So in all of these samples, the resistance or sheet resistance goes to 0 as you lower the temperature further, and the transition temperature can be as high as 2.2 Kelvin for the sample with a doping level of around 1 × 10⁻⁴ per centimeter squared. So this basically interface now is showing a superconducting behavior. And just remind you, the LLSTO system showed a superconductivity at a temperature of around 200 millikelvin. So this means this KTO interface is showing a superconductivity with TC about 1 order of magnitude higher than that. So this could actually bring us a lot of opportunities for doing quantum for doing superconducting device application or quantum qubits using superconducting qubits, because now you don't have to use dilution fridge to get to the superconducting state. At 2.2 Kelvin, you could just use a regular helium cryostat to achieve this temperature regime. So as I mentioned, we not only grow European oxide on KTO, we also grow lanthanum aluminum or LAO on top of KTO. We found that in LAO KTO system, the superconductivity can also happen. So this means this superconductivity does not depend on the specific oxide layers chosen to form the 2D electron gas. You can use any other oxide top layer. As long as you can get a conducting interface, you can actually achieve a superconductivity at a low temperature. So now you see that in both of these cases, the KTO substrate is 111 oriented. So we investigate also on KTO 001 surface, and you see that in this plot we have several samples, all of them grown on KTO 001 surface, including both European and lanthanum aluminum oxides. And in all of these samples, we do not observe any superconductivity. So this means the superconductivity itself is very interesting in that it cares about the crystalline orientation. So this could provide us a clue about the origin of the superconductivity, and it could be very interesting, right? Because anything that is directly related to superconductivity or the mechanism, that would be actually very interesting, because nowadays in condensed matter physics, people are intrigued by the high temperature superconductor. That is because the mechanism is still not understood. It is different than the BCS, the traditional BCS theory. So then any new system that can give you a strong clue about superconductivity, that would be a platform people would like to investigate, possibly to uncover new mechanisms responsible for superconductivity. So let me continue. So we further did some magnetic transport measurement on this interfacial superconductor. So we did the outplane magnetic transport. Basically, here we can measure the critical field as a function of temperature. So this is the in-plane, out-plane. Now, when we apply a magnetic field in the same plane, we found that the superconducting transition is robust against the in-plane magnetic field, meaning the critical field is significantly higher. You see that at 0.1 Kelvin, at even a 14 Tesla field, there's no sign of suppression of superconductivity. While for outplane, at 0.1 K, the transition, the critical field is around 1.7 Tesla. So then by doing this measurement, we can determine the Landau coherence length, which is about 13 nanometers. And further, using the in-plane critical field measurement, we can determine the thickness of the superconductor, which is about 5 nanometers. And this 5 nanometers is smaller than the Landau coherence length, which is which tells us that this superconductor is two-dimensional. So we further did the critical current measurement near the transition temperature. You know, for a 2D superconductor, there is an additional phase transition called BKT transition, and this is due to the formation of vortex, anti-vortex, or dissociation of that in two-dimensional, and that can create a power law dependence of voltage on current. So we found that this system indeed showed a BKT transition, meaning near the transition temperature, the V is proportional to current cubed. So this red line is the temperature. This is a cubed dependence, while this happens just at around the temperature where the sheet resistance is 0. So later on, we did a further measurement, and further with more samples, we found that the superconducting transition temperature on this KTO 111 surface is proportional to the carrier density. So here, the carrier density is measured using the Hall effect at a temperature of 10 Kelvin. You see that this black arrow showing an increase in 2D, while at the same time, the superconducting transition temperature also increases. Surprisingly, we also found that for KTO 001, as I just mentioned, there's no superconductivity. So there's no superconducting transition. So we found that for KTO 110 interface, there is a superconductivity happening. However, the maximum superconducting transition temperature is limited to around 1 Kelvin, which is half of that of the KTO 111 interface. You see that. So when we plot the TC versus N2D, we found that for KTO 111 interface, it shows a linear dependence, basically TC on N2D. While for other interface, for example, KTO 001, there's no TC, basically 0. While for KTO 110, it is showing an increase, but gradually saturating at a temperature of around 1 Kelvin. So you see that depending on the crystalline orientation, the superconductivity is quite different in terms of TC. So as I mentioned earlier, this should give us a strong clue about the origin of the superconductivity. So later on, my collaborators will basically doing the theoretical part of this work. We found that with our collaborators, we found that the transverse optical mode, or TO1 phonon, could be responsible for producing this striking interfacial superconductivity. So just remind you, the transverse optical phonon is just basically you have this is the oxygen p orbital, and this is the d orbital on the b side. Once you have a transverse movement phonon, so then there will be an induced hopping. So this is because that, so suppose here you have dxy and the py and dyz orbital, and in the ideal case, when there is no phonon, so they are in a straight line. So these orbitals are orthogonal to each other. So that means the hopping is prohibited. Now you have a transverse optical mode phonon, then these are no longer at the center. So this means mathematically they are no longer orthogonal to each other. So there will be a hopping between these two orbitals and eventually to this d orbital. So basically this transverse phonon can induce a hopping between different d orbitals, which would otherwise inhibit by the orthogonality of the orbitals, right? So because of this transverse optical phonon, we found that the electronic structure is modified, and there is a Rashba-like splitting at the KTO-111 interface. And in particular, we found that using this coupling, we can reproduce the linear dependence of the TC on carrier density. And at the same time, the TC on KTO-001 surface is vanishingly small, which is consistent with what we found experimentally. So just to give a little more explanation why this mechanism could produce a striking crystalline orientation dependent copper pairing or superconductivity. So this is again the KTO-111 surface, and in this case, the 3D orbitals and dxy, dyz, and dxz are all degenerate. They have the same energy. So this means they could couple strongly by the TO1 phonon because they are degenerate. They have the same energy. So once there is a TO1 phonon, the electron can hop from one orbital to the other. And further, you see that eventually for the KTO-111 surface, adjacent tantalum atoms are from two different layers. Basically, the red and the green color represents the two layers, and we found that the tier 1 phonon can couple adjacent layers of d orbitals in the tantalum site very effectively. However, if the tantalum oxide are in the same layer, just because of the symmetry, the tier 1 phonon coupling is very small. So now you see for the 001 surface, because 001 surface, all the tantalum sites are on the same plane layer. I mean the adjacent tantalum sites are from the same layer. So the tier 1 phonon coupling is very small. And also, this is also because the quantum confinement, the dxy orbital has lowest energy. So there's a splitting between dxy and dyz, dz orbitals. So there's only one orbital left in the lowest energy. So then the hopping between these orbitals are suppressed by the lifting of this degeneracy. So this explains why the couple pairing or the superconductivity is very weak for this KTO001 surface. Now for KTO110 surface, we found that, you see, along this orientation, around this axis, the y-axis or the vertical axis, you see all the adjacent sides of tangent are coming from the same layer, meaning the coupling, tier 1 phonon induced coupling is relatively small, while in this horizontal direction, they are coming from adjacent layer, so which can produce a effective coupling from tier 1 phonon. And so this explains why for 110 you can have a superconductivity, but the strength or the TC is lower than that for the KTO111 surface. And this is also because the degeneracy for this 110 is only partially lifted. You have now 2 orbitals left in the lowest energy in comparison to the 3 orbitals with the same energy. So with that, I'd like to summarize for my first part. And I explained that we found for KTO111 surface, we can achieve a superconductivity with the TC as high as 2.2 Kelvin, while for we further found that the TC is highly dependent on the crystalline orientation, with specifically with TC being linearly dependent on the carrier density for the KTO111 surface. So we found that the copper pairing via tier 1 phonon could reproduce the key experimental results. So this concludes my first part. Let me know if you have any questions. So I will continue to talk about the second part, which is about the electric field control of Magnum spin current in chromium oxide, which is so chromium oxide is a classical antiferromagnet, and also it is an insulator. So in recent years, antiferromagnetic materials becomes very interesting in spintronics research. So this is mainly because unlike ferromagnet, the near axis in antiferromagnet is quite robust against any stray field or any basically environmental disturbance. And also they do not produce any stray field because you have 2 magnetization from the 2 sublattices are fully compensated. So you do not have any stray field. So both of these properties are very desirable for spintronics application. So now in order to basically to be able to apply these materials, antiferromagnet, in spintronics application, the first task is to be able to manipulate the near axis. So the near axis could be used as the information, right? The 0, 1 information bit. So showing on this slide are 2 examples of using of controlling the near axis and how to read the near axis. So in the up part is iron basically FeRH rhodium. So in this case, it is a metallic at a high temperature, and also it is a ferromagnetic at a high temperature. Turns out that once you lower the temperature to sufficiently low, eventually this material shows an antiferromagnetic phase. So people can actually use field cooling to tune the near axis with two different orientation by applying a field at a high temperature and then lower the temperature. So with the field at a different orientation, you can actually manipulate the orientation of the near axis. So then people use the anisotropic magnetic resistance in the antiferromagnetic phase to read out the direction of the near axis. Basically, the high and low resistance corresponds to different orientation of the near axis. So shown below is another application of antiferromagnet, and this is a copper manganese arsenic system, and this is also metallic antiferromagnet. People in this case, use a spin-orbit torque to manipulate the near axis. And in the end, people also use AMI effect to read out the direction of the near axis. So you see, in both of these cases, people are using a AMI effect, which use a current to measure the resistance. And in particular, for this case, people may need to use a very high current to induce strong spin current to tune the near axis. That could be very, very power hungry and not good for low power application. So the experiment I will be talking about is based on spin-Seebeck effect, and in microscopically, this spin-Seebeck effect is related to spin pumping. So basically, showing in this cartoon, once you have a resonance or the precision of magnetization in a ferromagnet, and because of the exchange coupling between the ferromagnet and the conducting electron in adjacent material, this precision of magnetization can inject a spin current into this metallic material. As a result, there will be a spin current flowing across this interface due to this precision of magnetization. So turns out that once you use a heavy metal, this spin current can be measured using a inverse spin Hall effect. Because of the large spin orbit coupling, this spin current can be deflected towards one direction. Basically, you get a charge current, which produces a large voltage. So since its discovery, the spin-Seebeck effect or SSE, people have found that one can observe this spin-Seebeck effect in a diverse materials. So let me remind you, here, spin-Seebeck effect, we use a thermal excitation to excite a precision of magnons. So, spin pumping, people use the microwave to excite a ferromagnetic resonance. Now, in spin-Seebeck effect, you use heat to generate a magnons, and magnons can also produce a spin current flowing across the interface. So people have found that this SSE can be observed in a diverse material system. For example, in ferromagnet YEC PT system, and also in magnet diferrite PT, which is here, this is a antiferromagnet insulate system. People can also use measure a spin-Seebeck effect in some paramagnet, such as gadolinium gallium garnet or GGG. This is a paramagnetic material. It does not have a spontaneous magnetization or any near axis. Turns out that this is actually a frustrated material, and we found that this frustrated magnet at low temperature can show very unusual response of the spin current, which could be a probe of the for the shorter range ordering in the frustrated magnetic system. So let me describe the device structure used in our experiment. So we use microfabrication to fabricate the device. We have a heater on the top, and then we have a insulator which isolated the heater from the magnetic materials, and we also have a spin detector. Typically, we use platinum, and this could be used to detect the spin current, which is a heavy metal. We run a current in the heater, and then we use the double harmonic to measure the response of the spin current to the heater. So the materials we were interested in is the chromium oxide, or chromium 2-3. So just remind you, this is a classical antiferromagnet. In particular, when this material is grown along the 0001 orientation, there will be the two sublattice magnetizations will be pointing up and down, and they actually can form a uncompensated sublattices. This is because these two sublattices are grown simultaneously during material growth. So that means even though this is layered structure, and because these two sublattices can only grow simultaneously, in the end, even though the bottom surface is flat with just a single sublattice with spin pointing down, and even though the top sublattice is rough, but still the sublattice can be just the other sublattice pointing in the opposite way than the sublattice at the bottom. So this means the top and bottom surfaces belongs to the two different sublattices of this chromium oxide. So this is the device structure. So in the experiment, we grow this chromium oxide on sapphire substrate 001 oriented, and we first grow a platinum on top of sapphire, which is used as a spin detector, and then we grow a chromium oxide, and this chromium oxide is sandwiched by another platinum layer, which in both of these cases we can use top and bottom platinum to measure the spin current. We could also use these two electrodes to apply voltage across this interface, across the chromium oxide layer. So at the top, we have a heater, as I just described earlier, which can generate a temperature gradient in the vertical direction. So now, once we turn on the heater, and as we apply a magnetic field, so showing in this plot is the response measured in the platinum layer as a voltage as a function of the angle of magnetic field. So you see there are different traces, different lines, data points. So this corresponds to the magnetic field of different strengths from 1 to 6 Tesla. So you see there is a sinusoidal shape, basically a gradual increase of voltage as you rotate the magnetic field. And we found that for this response is reversible as you rotate the magnetic field from clockwise or counterclockwise direction, basically from 0 to 360 or 360 to 0. The traces are on top of each other. So as shown by the green, by the blue and the red data point for the 6 Tesla measurement. So we found that this response can be simulated very nicely using a micromagnetic simulation. We found that this shape corresponds exactly to the response of the horizontal component of the sublattices at the bottom surface of the chromium 2-3 as a function of the rotation of magnetic field. So by doing this simulation, we found that this specific response, this voltage, directly measures the sublattice of this magnetic moment in this chromium-2-3. So here we are measuring the bottom surface because we are measuring the platinum at the bottom of the chromium-2-3. So now, just now I showed you the measurement at up to 6 Tesla. As we increase the magnetic field, we see that the response shows a dramatic different behavior than the lower field. You see now the curve shows a sharp jump near the 180 degree. And once you rotate the magnetic field back from 360 to 0, the curve is no longer reversible, but showed a hysteretic behavior, right? So this can remind you some hysteretic behavior in some magnetic system, just like when you have a magnetization subject to an external field, and if that magnetization also experience a anisotropy, you will typically see a hysteretic behavior. So from the simulation, we found that this sudden jump is due to actually a spin-flop transition in this chromium-2-3. So once the field is above the spin-flop transition field, which is about 6 to 7 Tesla, you see this transition. And this behavior can also be nicely captured in our simulation, as shown in this figure on the right. So now, basically, we now achieve the first thing we have achieved is that this spin Seebeck effect can be used to characterize or measure the component of the sublattice or the magnetic components of the sublattice very precisely. So to show you further, we would like to measure the sublattice at the top surface of chromium-2-3. As I mentioned earlier, the top surface of the chromium-2-3, the top layer, corresponds to a different sublattices in this chromium-2-3. So then we found that in the top layer, the platinum layer shows a specific Seebeck voltage with different polarity than that measured in the bottom surface. You see that the maximum here occurs at an angle close to 0 degree rather than 180 degree. So basically, they show opposite behavior. So this is just because these two sublattices belongs to different, initially have different orientation, so they have opposite response to external field. And this is also true for the field above spin-flop transition. You see that the red curve shows this polarity, while the red curve shows the opposite polarity in the top platinum layer. So now I would like to do one more thing. Suppose initially the bottom surface spin is pointing up, the top surface is pointing down. Now they have the opposite polarity. Now can I do a manipulation such that I switch the orientation of these two sublattices so that could this response be also switched if our theory is correct, right? If our explanation is correct. So to do that, suppose initially you have sublattice A and B pointing up and down respectively. Now we apply a high magnetic field. This magnetic field is high enough to induce a spin-flop transition. And then we rotate the magnetic field by 180 degree. So then this flop state can follow the orientation of the magnetization of the magnetic field. And then we reduce the magnetic field. Eventually, we can flip the orientation of these two sublattices. So by doing this manipulation, we can achieve, we can see that how this polarity changes. Now this is before the manipulation. After the manipulation, we see that the polarity is switched simultaneously for both the top and the bottom surface. You see that. So this proves that this polarity difference is just due to the difference in the orientation of the sublattices. So now we show that we further found that this spin current. So what we measure here is due to the Magnum spin current, and because the chromium-3 has a special property which is called the magneto-electric coupling. Basically, this means a magnetization could be induced by applying an electric field along the z-axis. This is due to the special crystal lattice of chromium-3. And people found that by simultaneously applying both an electric field and a magnetic field, people can actually switch the orientation of the sublattices. So this provides an opportunity that one can manipulate the sublattice of the chromium-3 by switching by using an electric field. And further, because chromium-3 can produce a Magnum spin current, this means we could use electric field to manipulate the Magnum spin current directly, right? This could be very advantageous for spintronics application. So in order to investigate that, we actually use the same device. Now we can apply a gate voltage between the top and bottom platinum layer. So we use a magnetic field of 8.5 Tesla, which is very close to the spin flop transition. So now at 0 volt, you see a partial switching. So this means just because the field is very close to the spin flop transition. Now this bias voltage is 0 volt. Now when we apply a voltage of negative 15 volt, you see that the response is completely changed. Now you see a reversible behavior with continuous dependence of spin-specific voltage on the orientation of magnetic field, just like the measurement done at a lower field, right? Now, when we apply a positive gate voltage of 15 volt, you see a sudden jump happening, and the curve is no longer continuous and no longer reversible. Rather, you see a hysteretic behavior. This is just like the measurement done at a high field above the spin flop transition. So, however, here we are doing the measurement at the same magnetic field. The only difference is the voltage applied across the thickness of chromium-3. So we further did the measurement near the transition, basically near this flop transition. We found that the transition angle can be tuned by applying a gate voltage. You see, from negative 80 volt to positive 24 volt, the transition temperature can be tuned by more than 10 degrees. So the x-axis is the angle for the magnetic field. So this means we could do the measurement at a fixed field angle while simply applying a gate voltage, and this gate voltage could be used to introduce the transition directly in the Magnum transition in the specific voltage. So this is indeed the case. So in this case, we apply a magnetic field at a fixed angle, and initially the spin-specific voltage is at around 150 nanovolt, corresponds to one orientation. Now we gradually increase the gate voltage without changing the magnetic field. We see that the spin-specific voltage can be driven to transition to another state, which has 0 volt spin-specific voltage. So now you see that we can achieve a gate voltage induced transition in the spin-specific voltage directly. So this, as I mentioned, could be used for further spintronics application. So with that, I'd like to conclude for my second part. So I talked about the spin-specific effect can be used to sense individual sublattice magnetization in an antiferromagnet, and we can control the polarization of the Magnum spin current using an electric field utilizing the magnetic electric coupling in chromium oxide. So this concludes my my talk. But with that, I'd like to thank all my collaborators. Without them, I could not finish all this work. So these are my collaborators from Argonne National Laboratory at Case Western Reserve University, Huazhong University, Institute of Physics at CAS, Peking University, Auckland University, as well as at UIUC. So with that, I'd like to thank you for your attention.
Yeah, thank you too. Yeah, good, in fact, excellent talk, Changjiang. Please, one second, please. Here. Not have questions chat. Oh, there's.
Can you see my screen?
Yeah, yes. Oh, does anyone have question? Alguém tem questão? Alguma pergunta? Okay, I have one question, please, Changjiang.
Sure.
In fact, foreground, the potassium tantalum oxide, it's not easy. Explanation more about the difficulty foreground this material, please.
Yes. So we use the growth, use the use the MBE to grow European oxide. So also use the PLD. So now there are following our work. People can use sputtering to grow a thin layer of aluminum on KTO. They can also achieve a two-dimensional electron gas that is superconducting. So yeah, if you have sputtering available sputtering unit, you can also grow aluminum on top of KTO, a thin aluminum layer.
Sure. Yes, very nice work, in fact. Excellent publications. Very nice. Any questions? Changjiang, thank you.
Thank you
again for accepting this invitation.
Yes, thank you for inviting me. It's my great pleasure to be able to present.
Sure, for me too. See you in another opportunity. See you soon, my friend.
Okay.
Bye-bye.
Bye.